Hi, my name is Thomas Sears. I'm from the Off-Road Robotics Research Group and the Ingenuity Labs Research Institute at Queen's University in Kingston, Ontario, Canada. In this video, I'm going to provide an overview of our paper, Mapping Waves with an Uncrewed Surface Vessel via Gaussian Process Regression. This research aims to find new ways to model dynamic phenomena. In many applications, this requires the deployment of many static sensors, but instead, could we deploy a single mobile robot to collect that same data? In our paper, we advance previous work through theoretical improvements and by deploying an uncrewed surface vessel equipped with inertial sensors in order to map the waves. There are two main contributions in this paper. The first is the further development of a spatiotemporal mapping technique from Gaussian process regression for a single mobile robot sensing a dynamic environment. This includes the selection of covariance functions and ways to initialize and constrain hyperparameters in the optimization process. The second is testing this technique with data from our uncrewed surface vessel on Lake Ontario. We describe the inertial measurement system and how this data is used offline to perform spatiotemporal wave mapping, the results of which match wave observations made through video and frequency analysis. Stick around for the rest of the video as I dive into more details about the research context, mapping technique, and field trials discussed in this paper. Mobile robots are powerful tools for understanding the environment. They can reduce effort, improve safety, and even enable new observations for researchers. It is therefore no surprise that there have been numerous efforts to see how we can use sensors and robots to gather this environmental data. Measurements, whether collected from a mobile robot or a static sensor, are vital to environmental surveys. The main difference is in the environment itself. Is the phenomena in study changing or not? When using a mobile robot, it's most common that researchers only consider spatial mapping. Examples of work mapping in space and time are limited and make use of model simplifications and robots without motion constraints. There remains an opportunity to relax these assumptions and see how mobile robots can truly create high-resolution spatiotemporal maps. A common factor is the use of Gaussian process regression techniques for mapping, whether for spatial or spatiotemporal phenomena. We propose that a Gaussian process regression workflow can be used to model dynamic phenomenon with measurements from one or more mobile robots. Gaussian process regression is a well-studied modeling technique. In this next segment, I will introduce its utility in mobile observations and mapping, and how covariance functions can be selected to map a dynamic phenomenon. The mapping process is mostly straightforward. We collect wave measurements and then associate them with a position and time taken from the onboard GNSS. That data is then fed into the Gaussian process regression model in order to create our spatiotemporal map. The modeling complexity comes up in the selection of suitable covariance functions and the optimization of their hyperparameters. Two kernels were selected based on previous work. First, the squared exponential kernel evaluates nearby measurement correlations as well as long-term trends. The second is a periodic kernel, which captures repeating structures in the data. Both of these covariance functions are evaluated across all input axes, position and time. We've chosen to combine a number of these kernels together. We preferred the product of sums combination due to performance and design intentions, which are discussed further in our paper. With the mapping workflow set, we can now move on to field experiments to collect the data and test our spatiotemporal mapping capability. The Otter USV is not a large vessel. In coastal environments, even small waves impart a significant disturbance on this vehicle, which is quite visible in this field trial video. But this offers an opportunity to measure wave action by recording the vehicle motion with inertial sensors, so we have designed and added an inertial measurement system onto this vehicle for these trials. We also take advantage of the fact that at rest, the water surface is perpendicular to the force of gravity. Using the gyroscope and accelerometer measurements, we can use the USV's orientation to determine the angle of the water and the presence of waves. Using the built-in control station software, the USV was set to follow a circular path approximately 20 meters in diameter at a constant speed of 1 knot or about half a meter per second. Over the course of a 4-minute observation period, position, time, and inertial measurements were logged at 10 Hz. This data was then used to create a spatiotemporal map for a 25 by 25 meter region that fully encapsulated the circular path. Now, we are currently lacking a robust spatiotemporal ground truth for the waves, so we instead compare the spatiotemporal map against a single point observation that provides the frequency spectrum of the waves. This dataset shows a peak power around 1 Hz. After optimization, the hyperparameter from the temporal periodic covariance function was 0.87, which can be directly translated into an estimated wave period of 0.87 seconds, or roughly 1.1 Hz, which is a close match to our single position observation. Looking at snapshots of the spatiotemporal map, we can see that the periodic trends of the waves is captured, but predictions are limited to the region nearest the vehicle. Investigations into broadening these predictions is ongoing. To close, here are some of the conclusions that we drew from our work. We saw that waves can be measured using inertial sensors placed on board an uncrewed surface vessel. Using a combination of squared exponential kernels and periodic kernels, we were able to use Gaussian process regression to make a spatiotemporal map. We saw that the results of that mapping matched qualitative assessment from video as well as frequency analysis. Future work includes taking that wave map and feeding it back into the control system of the uncrewed surface vessel in order to improve control performance. Thank you so much for listening. If you have any questions, please get in touch or check out our paper for all of the details. Thank you.